Good morning, everybody. So, in today's class, we are going to study the next aspect of part design, that is wall thickness. In the previous classes, we have started the studying aspects, different aspects of part design, which includes tolerances, allowances. In just recent class, we have completed the allowances. There are two types of allowances we have studied. One is shrinkage allowance, another is draft allowance, and after that we have also concentrated on the next aspect, that is the rib design. So what is the rib, what is requirement of rib, how it is used for increasing the structural stability of your component, then what are the guidelines for selecting the rib, what are the guidelines for deciding the thickness of rib, what are the guidelines for deciding distance between two ribs, height of rib. All these aspects we have covered in the previous class. Also, it may be there may be chances to ask the MCQs on the these guidelines also that I told yesterday. For example, rib thickness of the rib is around 60 to 80% of the wall thickness of the component. So thickness of rib will not match with the thickness of wall of the component. If wall thickness is 1 mm, the rib thickness may be 0.6 to 0.7 mm. So 0.6 to 0.8. So 60% to 80% of nominal wall thickness. This will be the consideration in the rib design. Now in today's aspect, very important concern will start, that is wall thickness. Wall means whatever component you are going to manufacture, whatever part you are going to prepare, what will be the part of that part's thickness, that is called as the wall thickness. So one important thing I want to repeat here once again, we are dealing with plastic components, that is polymers. No doubt we are going to shape it by melting. So once you melt it, it will be injected, it may be poured, it may be blowed, it may be extruded, whatever may be. So these parts, as they are polymer based, no doubt they are going to cool by air and water. But once you cool the outer surface, it will solidify. What about the inner part of the product which you are going to manufacture? As polymers, plastics are bad conductor of heat. You may find that if suppose this is the thickness, if this is a thick part made up of polymer, outer side it may become cool, you may find it becomes solid, but inside you may find, see now this I am showing the water now, here this is just one paperweight, this is one paperweight, inside this how the liquid remains as it is, same way the liquid molten plastic inside remains as it is, and then it is very difficult to extract the heat from that molten plastic through the solidified wall of the polymer, because they are bad conductor. Hence, it is always preferable to have minimum wall thickness, because cooling time is directly proportional to square of the wall thickness. This may be asked in the MCQ or objective type question. Cooling time is directly proportional to square of wall thickness. So higher the wall thickness, cooling time is proportional to square of it. Imagine. So even you increase the wall thickness by 0.1 mm, you will find tremendous increase in the time. If earlier cooling time is supposed to be 3 minutes and you just added 0.1 mm thickness, it may be doubled. It may become 6 minutes. So this we are thinking in the terms of cooling time, because if cooling time increases, cycle time increases, then cost of the process increases. Everything depends upon each other. That's why you should keep the wall thickness as minimum as possible. Okay, so you write down this and write one statement. one of the most important rule of part design, one of the most important rule of plastic part design is wall thickness should be less and uniform throughout the part. One of the important rule of plastic part design is wall thickness should be minimum and uniform. Minimum and uniform throughout the part. Full stop. Generally, it is kept between 0.1 mm to 5 mm. Generally, it is kept between 0.1 mm to 5 mm. Now, why wall thickness is less? Why? Why wall thickness be less? So, first thing, for reducing weight of component. This may be MCQ, that's why I'm writing it on blackboard. First, for reducing weight of the component. Second, for faster rate of cooling. Second, for faster rate of cooling. And third, higher productivity. So I repeat, why wall thickness should be minimum? Wall thickness should be less or minimum for reducing weight of the component, for faster rate of cooling and higher productivity. So if you will follow this, then your component will be durable, your component making process will be easy. Making process will be easy. Why? Because what component you made, it will be light in weight, it will perform well as designed, and then faster rate of cooling will cause faster production rate and productivity increases. Means if you are planning to manufacture 10,000 components in a week, that 10,000 may become 15,000 components in a week. Now, there are many such cases where you can't keep your wall thickness minimum. So there is a shape limitation. So some parts are there where there is a limitation of shape. You must follow that shape. Otherwise, it will not fit there. If it is constraint, if shape limitation is your constraint or size limitation is your constraint, how to overcome this? By following the minimum wall thickness. Let us see this. Write down next line. In case of limitation or in case of constraint of shape and size, I hope you have written this. I am going to erase it now. In case of constraint of shape and size, comma, the design is little modified by keeping uniform wall thickness, without disturbing size and shape. How it is possible? Check. Without disturbing size and shape. Now see, so as I was explaining you, limit size or shape constraint. This is my requirement of plastic component. I want to produce this. See how thick it is. Thickness is very high. Then I don't, without disturbing shape and size, you can keep uniform wall thickness. Till now, this question is open to you. I don't want to change the shape, outer shape, and I have to keep uniform thickness. I don't want to change the size also. Who will tell this answer? What modification you can suggest? Ajinkya Jadhav, roll number 23. Ajinkya Jadhav. Hello, where are you, Mr. Ajinkya? Then Avinash Vankalas, roll number 69. Avinash Vankalas, roll number 69. Roll number 69. Roll number 73, Prasad Magji. Roll number 73, Prasad Magji.
Yes, sir.
Please answer to this question. Without changing. So one figure is in front of you. I have drawn on the board.
Yes, sir.
This is the plastic component. There is a dimension limitation constraint. Without changing the outer dimension, how can you reduce the thickness of this component? Because this high thickness, you can't get this product easily because of solidification problem. Can you suggest, assume that after 3-4 months you are working in one of the industry and such problem you are facing. How can you suggest as a design engineer? Tell. Prasad.
Yes,
sir. If it is wrong or right, you don't think. Just put your idea here. Without changing outer dimensions. I'm intentionally giving stress on the word outer dimension. How can you reduce the weight of this component? By keeping uniform wall thickness. Any idea?
no, sir.
Give stress to your brain. We engineers are known for higher IQs. Okay, so we have to give stress. Then only some outcome will come. Onkar Gadge is there. Onkar Gadge. So somebody put here. Okay, middle portion can be cut down. Cutting will cause problem because if it will become ring, then compression may cause pressing of the component. You are 50% correct. Your answer is 50% correct. Nagras. We can make hollow. So hollow again, from where you are going to put the core, and these are molds. Okay. So it is not as like sand casting. This is a metallic mold and there is limitation of sliding cores. Both answers are 50% correct. Pranil's answers and Girish answer. Your answer is 50% and your answer is 50%. Now see how I am modifying it. See here. So this component, if you see, draw it from the front view. I have shown the arrow. So what will be the front view of this component? This simple rectangle. No doubt, here is one line. There is no line here. Only one line will be here. Now, I want to decrease the weight of this component by keeping uniform wall thickness. Now, this is the wall thickness. Okay. How can I modify it? See. So what answer you said is 50% correct. That's why I said I can cut it, but not complete hollow. I will make it in this way. So this portion now this is not complete hollow as said by Mr. Pranil. This is not complete hollow. From inside there is one vertical strip at the middle. Wall is there in between. Just try to imagine. So this is not hollow. From this side and this side at center there is a wall like this. So some of the area get removed from this side. So you have to use such core plates while making the component. So if I will use simple mold, you will get earlier shape. Okay. So this will be modified. Earlier is here. This earlier shape is modified here. So by removing this material means there is no question of machining or removal material. Core plates are used in such a way that plastic will not reach in that area. And this will be your modified. Earlier and this is modified. I hope you understand. So there is no complete hollow part. So some material removed from this side, some material removed from that side. And everywhere you will find uniform wall thickness. Check. Everywhere. Are you getting? Because we have this dimension constant. We can't reduce this dimension. We have dimension constant. And in that way, you can take this. So this is your thickness now. This is width. You don't consider this as a thickness now. Thickness is this. So everywhere you go, thickness of the component, and in middle wall, this wall is also same. Draw this figure. I hope you understand this. This is most correct. See here, as per the drawing convention, this figure is most correct. So earlier I have shown dark lines, now I made it dotted. So that's why these dotted lines represents that there is one wall in between. So modify your figure accordingly. Make correction. Please make correction here. Because these two lines will be dark line as it is, because it is present here. Now, I hope you have drawn this. I'm going to erase it now. Now, if this is the component, there is a shape limitation and dimension constant. How can you modify it as per requirement of minimum wall thickness? Apply same logic here also. Modified to see, I'm not changing the outer dimension. It is as it is. You can maintain this. Draw this. Earlier part drawing can be modified to this way. Now, next aspect is design of corners. Now pay attention. In case of corners, so you have studied machine design and you have studied stress concentration. You know that if sharp corners are there, it may cause the stress concentration and generation of the stresses, and crack will initiate there and it will break. Here, region of corner is not according to that theory. We are thinking first to manufacture the component, to mold the component. So our aspect of design of corner is in the view of manufacturing process or molding process. So that part which you are using, generation of stresses and crack, that is different aspect, which may be in actual working condition. But here the thing is that when you are going to make the component, when you are going to process the component, if your sharp corner will be there, it is very difficult to produce the component. Why? Because at corner, the wall thickness increases 1.4 times. I repeat, if you have sharp corner in your design, wall thickness at the corner increases 1.4 times of the nominal wall thickness. So wall thickness increases means cooling time increases, then productivity decreases. That's why here sharp corners are avoided in the design itself. Sharp corners are avoided in the design of component itself. See what I am saying to you. This is your component. And if this is T, wall thickness, then if you see the corner, this will be the thickness considered, and which is 1.4 times the wall thickness. 1.4 into T. So if this wall thickness will be almost 1.5 times more, it will cause the decrease in the rate of solidification and in turn decrease in the productivity. That's why if you modify this design in this way, you will have uniform wall thickness. This is T. This is also T. We are not talking in the terms of stress concentration, maybe generation of crack. That aspect is totally different. Here, manufacturing aspect we are talking about. When you are going to solidify your component, the thickness will affect the cooling rate. So that's why, while designing the parts, sharp corners are avoided. You can write this statement. Wall thickness increases wall thickness increases 1.4 times more 1.4 times more than nominal wall thickness at the corners. Full stop. This will result in differential shrinkage. Means shrinkage here will be different, shrinkage here will be different, and longer cooling time. Full stop. Hence, sharp corners be avoided. Now, at the rib junction, when there is a rib junction, there may be cause contraction. That's why there also the thickness of rib is maintained at 60% to 80% of nominal wall thickness. So that maintaining the thickness 60% to 80% will also be important concern while solidification is there at the junction. That's why it is always preferable to keep rib thickness 0.6 to 0.8 times as that of wall thickness. I will show how there is a volume contraction at the junction. I hope you have drawn this. If you will not follow the pattern of 60% to 80% thickness of rib, in this way, there is a contraction. Sink marks. Here, this thickness is reduced and then solidification will not affect. Similarly, internal corners, draw this. So it is very simple thing that in case of wall thickness and in case of rib, it is always better to maintain that relation. The relation is that 60 to 80% of the wall thickness. Then you can avoid the sink marks and other problems. One minute. Now, next one is design of undercut. Pen is creating the problem. No, no, no. Design of undercut. Now, undercut, this is important concept. I hope you are remembering. Next, I will explain you. So, design of undercut means what? Now, if you manufacture the any of the component, so in that component, removal of the component from the mold is important aspect. In case of patterns, removal of pattern from the mold. So if pattern will not be get removed from the mold, pattern may cause breaking of the mold wall, and you will not achieve your desired shape of that cavity. Here, this concept is different. Here, your actually molded component, you are going to remove from the mold wall. Actually molded component. Design of undercut. Okay, so if this is one of the mold half, this is another mold half, you are going to close this mold. Component is inside. If you open it, the product which is here, you are going to remove by ejector pins. If it is having undercut means what? Some extended part which gets locked in the mold. For example, now see this figure. If you are going to remove it in this direction, if you are going to remove it in vertical direction, in this direction, this part is called as undercut. This is called as undercut, which may get work as an obstacle for easy removal of the component. Then, In case of metallic parts, there was problem. In case of metallic part, you can't remove it. But as this is plastic, so strippable. Strippable means what? See this. I hope you are observing this, which is used for putting or locking in the pocket. So now this is strippable. Strippable means you can strip it in this way for just purpose of removal. That's why we are providing the interference pits here. Actually, the inside ring is of little smaller dimension than this hole and shaft. This concept you have studied in that AMQC subject. So here now it is not fitting well, but when I am pressing it, it is interference pit. It is called as interference pit. No doubt. So this part is a strippable. See, you can look this. So I can easily strip it for removal purpose. So in such case, if some undercuts are there, you can strip it for removing purpose. Undercuts are nothing but the obstacles or extended parts in the work component or your workpiece which may cause difficulty in removal with the help of ejector pin. I repeat once again, undercuts are nothing but surfaces which are perpendicular to ejector pin movement or mold movement. Surfaces which are perpendicular to ejector pin movement or mold movement. In that case, you can use some sliding cores to avoid this undercut. You can use this sliding core, or if possible, you can make it of small thickness which can be strippable while removing the part. Okay, this is just simple concept of undercut. Write down this. Undercut in case of plastic molding. Undercut in case of plastic molding are possible, but it require sliding core and split molds. But it requires sliding core and split molds. The requirement of core pull can be avoided by providing shallow undercuts. Which often may be strippable. Strippable means you can just mold it. If such undercuts are strippable, the other half of the mold needs to be removed. Just a minute. Okay, so this is as far as the aspect of wall thickness, then design of undercut, and today we have seen this. After wall thickness, we have corners and undercuts, corners and wall thickness. This part is covered today as an aspect of part design. Now two more aspects are remaining: holes and inserts. That may be covered in the next class. So you have to remember all these aspects, because once these aspects are over, we are going to take the actual design part, how to design the component. Okay, that is plastic component. Today we will stop here. Thank you.